Hello, student. Welcome to the session 21 of this paper, Electricity and Magnetism. In this session, we are going to learn what are the scalar and vector fields, and we are also going to study the gradient of a scalar function. And on recap, already you have studied all these things like scalars, vectors, and vector fields, and the concept of operators. And learning objective of this session is that we are going to study the concept of scalar fields, the concept of gradient of a scalar field, and the meaning of the del operator. And session outcomes. At the end of this session, you should be able to tell what are the scalar fields, what is the meaning of the gradient of scalar function, what is the action of a del operator. And next, first we will going to study what is the scalar field. Before going to the scalar field, first we will learn what are the scalar and vector quantities. So there are two types of physical quantities in physics. One is called as the scalar quantity, other one is called as the vector quantity. The scalar quantity is a one which is having which is having only magnitude but no direction. Example for that kind of such type of quantity is that temperature, pressure, density, electrical potential, mass, length, etc. are the examples for the scalar quantities. And there are other type of physical quantities in physics. They are called as the vector quantities, and these quantities have both magnitude and direction. And the example for these quantities are velocity, acceleration, electric field intensity, magnetic field intensity, force, etc. So by learning these two things, again we'll move back to the our topic, scalar field. Now I am going to explain what is this scalar field. Any physical quantity which can be expressed as a continuous function of the position in a region is called as a scalar quantity. The region specifying that physical quantity is considered as its field. The physical quantity may be either a scalar or vector. And there are two types of scalar fields. So first, the scalar field means that physical quantity is a continuous function and it is a scalar quantity distributed around a point. For example, take a point charge. Around a point charge, the electric potential is distributed. This electric potential is an example for the scalar field. And similarly, there is a vector field. Vector field, in case of a vector field, every point in that field or in that region is having both magnitude and direction. That kind of quantity is called as the vector field. And example for this scalar fields, I have some examples for the scalar and vector fields. And here you can see this diagram in this picture. We have the picture of world it is, and this number indicates the temperatures at different regions. So it is the best example for the scalar fields, and this number indicates temperature at that particular position. And another example for the scalar fields is the contours of the world. So this color represents surface temperatures, and contour line shows the constant temperature. So here different colors are there. In that different colors, temperature is constant. So these are the best examples for the scalar fields. So another example is there for the scalar field. It is the pressure variation in the atmosphere. The pressure is different at different positions of this atmosphere. So it is a pressure gradient is there around the surface of this earth. So it is also a good example for the scalar field. Again, I will move back to our topic. So now you understood what is the meaning of the scalar field. So you also understood what is the vector field. And in a region of space with a scalar quantity is continuous and is defined as a single value at every point of the position variable is called as the scalar field. So this scalar field phi is represented by phi of x comma y comma z, and where this phi r is the position vector. So in a scalar field, there are a number of surfaces upon which the physical quantity has a definite constant value and is known as a level surface. So to understand what is the level surface, we can refer to this diagram. So this diagram. So here in this diagram, this different color indicates one temperature, the presence of one temperature. Here color is changing, so temperature is different. So everywhere as the color is changing, the temperature is changing. So one color represents one temperature. So these are the best examples for the level surfaces. So I will move back to the topic. So now we have understood what is the meaning of level surface. Level surface means that is the surface where that physical quantity is having some constant value. Then we will understand what is the gradient of a scalar field. So consider the position vector. Consider a point P in the scalar field having a position vector like this, and this point is connected to the origin. So this R represents a position vector xi plus yj plus zk, where xyz are the directions, and this function is represented by this function phi of xyz, and I can refer to this diagram to understand for more understanding of the thing. So you consider a surface here like a sphere. I think that you have kept a charge at the center of the sphere, and the surface of the sphere is a level surface. Is again an example for the best example for the level surface. And here is a point P, and this is connected to the origin, so that is given by the position vector. So this function phi of r is equal to phi of x y z is now a scalar field distributed around a point or around a region, in a region around a point. Then we can partially differentiate this function. First, we can be, because there are three variables are there, so partially derivating this function with respect to x, with respect to y, and with respect to z. So three partial derivatives we are getting: dou phi by dou x, dou phi by dou y, dou phi by dou z, and dou phi by dou x is component of this scalar field along x-axis. Dou phi by dou y is the component of the scalar field along y-axis, and this is the same thing along the z-axis. So we have three partial derivatives or three components along x-axis, y-axis, and z-axis. To get the total effect of all these three components, we are adding all those components vectorially. So that is written as a grade phi. So this grade phi is equal to I into dou phi by dou x plus j into dou phi by dou y plus k into dou phi by dou z. So then separate the phi, take out as it is common, and write whatever it is there, excluding this phi. So excluding this phi is this quantity, and this quantity is represented here as a del, and the symbol del is called as the vector differential operator, or the simply del operator. So del is not a vector but an operator which obeys the laws of vectors. So this del operator, actually what it does, when it acts on a scalar quantity, that converts that scalar quantity into a vector quantity. Is such an operator it is. So this vector del phi is called as the gradient of the scalar. So that is why the gradient of this scalar. So this del phi is a vector normal to the surface phi of x, y, z, constant at every point. That means this gradient of the scalar field is in a vector. Scalar field is a scalar quantity, but when this del operator operates on that scalar quantity, that quantity is converted into a vector. So this del phi is a vector, and which is always normal to the level surface at a given point. And if it is if this n is a unit vector normal to the surface in the direction of increasing phi, and dou phi by dou t is the derivative, and it is represented in this way. And we'll see what are the properties of this scale gradient of the scalar field. This grade phi is a vector whose magnitude at any point is equal to the rate of change of phi with the distance along the normal to the level surface. Again, I am referring to this diagram. So it is a level surface, and this grade phi, this x-axis is normal to the surface of the sphere. So it is a gradient of the scalar field in x direction. So y-axis, similarly, y-axis is also normal to the surface of the sphere. So it is the y component of that gradient. So similarly, z-axis is there. Z-axis is also normal to the surface of the sphere. So that is also the gradient of the scalar field. So therefore, so this gradient of the scalar field is always a normal to the level surface at a given point. And this is already explained. So the gradient of a scalar function phi is a vector whose magnitude at any point is equal to the maximum rate of change of scalar function phi with respect to space variables, and has the direction of that change. Again, this diagram is very useful. So you see here, dou phi by dou x represents the rate of change of that physical quantity along the x-axis. For example, again, if you are keeping a charge at the center of the sphere, and potential is decreasing if you are going either in the x direction, y direction, or z direction. So that decrease of potential along x direction or y direction or z direction is indicated by this gradient. So that is the physical meaning. So this del operator must always be operated on a scalar function. So it is not used to operate on the vector function. It is always used to operate on the scalar function. Next, so there is a relation between the electric field and potential, as you know. It is given by E equals minus grade V, gradient of V, where this V is the potential, but E is the electric field intensity. So it is written in the operator form as minus del V. So if suppose if Ex, Ey, and Ez are the components of this electric field intensity along the x, y, and z directions, then they are written in summation form in this way. And as from this equation, it is equal to minus del V. So minus is the del, you put the del and multiplied by V gives this thing. And now equate the respective components on either side. What you are getting is that Ex is equal to minus dou V by dou x, Ey is equal to minus dou V by dou y, and Ex is equal to minus dou V by dou z. So these are the components. Ex is equal to minus dou V by dou x means it is the component of this electric field intensity along the x direction. That is given by the rate of change of this potential with respect to x direction. And similarly, Ey means it is the rate of change of what is that vector potential? Sorry, uh, potential in the y direction. So these are the Ex, Ey, and Ez are the components of this electric field along the x, y, and z direction. This shows that electric intensity at a point in electric field in a given direction is equal to the negative potential gradient in that direction. So the minus sign indicates that E points in the direction of decreasing V. So as you are moving either in the x direction or y direction or z direction, the potential decreases. So for that you have to write this negative symbol. So summary of this session is that now you have understood what is the meaning of the scalar and vector fields, and also you have studied the concept of the gradient, and also you have now understood what is the meaning of what is this del operator, and also you have came to know the relations between the electric field and the potential. So here are some MCQs. So the mathematical perception of the gradient is said to be slope. It is a slope. It gives the rate of change of physical quantity in one direction. So it is a slope. So the gradient of xi plus ya plus zk is 3. Why it is 3? Because you are differentiating this with respect to x, y, and z. So each time it gives 1, 1, 1. So 1 plus 1 plus 1 is 3. So the answer is 3. And the gradient of the scalar is a vector because it is the property of this gradient or the del operator. When the del operator operates on a scalar, it converts that scalar into a vector. So next, the relations between electric field and electric potential is given by E is equal to minus del V, as I have just explained. And if the electric potential at any point due to a point charge q is given by V is equal to q by r, then the electric intensity is given by E is equal to q divided by r cube into r. This already we have studied in PU level or BSc level. And this is the end of and these are the reference books so you can go through. And this is the end of the session. So